All right, why don't we get started? As you can see, I have the test twos finally, and at the break or whatever, you can pick up a copy. They're numbered, and there's a key as before. Okay, so in this sort of last real lecture, I'd like to talk about a stray topic that we haven't really touched on. Although I do this item sort of in CS61B, it's kind of important, at least for along the lines of the way I said some time ago that optimization is important because it allows you to do things right, to write abstractions and expect that they're going to get compiled in some reasonable fashion. Well, garbage collection is like that. It allows you to ignore certain otherwise inconvenient things that you would have to do in order to use heap storage freely. But let's first of all just consider, this is this is the characteristic of Java. It was also the characteristic of Scheme, characteristic of full Python, real Python, that there's no way of freeing dynamic storage. And instead, the runtime system takes it upon itself to keep track of storage that's no longer going to be used and to reuse it, right? Or perhaps to return it to the system, as the case may be. So this is an example. We're in some sort of a program. It does nothing but create a new list and returns its tail. Of course, this means that the head of the list there's no longer any way of getting at the head of the list. There's no variable that stays around that allows you to touch that thing. So you can get rid of it. Now, I said at this point Java's runtime, like Schemes, recycles the object. That's not quite correct. At some time after this point, Java's runtime can recycle it whenever it really needs to. So the question is, of course, how do we get this special effect? Well, first of all, of course, we can argue, let's kind of contrast this with C++ for a moment. In C++, there is no such thing. Instead, there are explicit instructions for freeing heap storage. Heap storage, by the way, remember, heap storage is this dynamic allocation where you determine there's a certain statement at which it comes into being, and where it disappears, well, that depends on the language. It doesn't go away at function boundaries or even thread boundaries, possibly process boundaries, although sometimes not even then. For certain kinds of persistent storage. So the question is, how is this accomplished? All right, well, you've already seen one method. We actually use it, or Horn uses it, and that's reference counting. Very simple idea. We'll simply have a bunch of, we'll simply keep track in every object of how many times that object is used, how many claims there are on the object. And when that number reaches 0, then you know you can free it. Okay, so how do you keep track of that? Well, we start out, if we imagine starting out in the situation on the left there, upper left, we have a bunch of list cells, or some kind of cell, I guess. And each one of them is pointed to by exactly one other pointer, by one other object. Starting up there with the variable x, and each list then points to one or two other lists, and that's how they all have a reference count of 1. If I now set y to x's tail, then that means that the variable, that means that the second list object on the top now has two things pointing to it. So how would you do that? Well, that obviously means that every time you assign a pointer into y, you must look at two things. One of them obviously is what is the pointer you're storing in there, and you have to indicate that that pointer now or that object that you're pointing to now has an extra reference. And you must also, this is a trick question because in this case you don't have to do anything else, but in general you must, when I set y to be the tail of x, when I set y to be anything, yeah? That's true, it does. So we have to make sure that, in this case, null, we could either have an object with a big reference count or something like that, but normally but with a null pointer, you just don't increment its reference count in that case. Okay, now if we now set x to y, and this is illustrated down in the lower right, the lower left, if we now set x to y, we increment the reference count on y, on the second object there. We now have 3 pointers to it. One of them is, so x, y, and also this object still. But we've also, by moving that pointer x, we've also taken away we've also taken away one of the pointers to the first object, the top left object. And because we've done that, that means that we can get rid of that top left object. In the process of getting rid of the top left object, just like if a variable goes out of scope, the variables within that object cease to exist, and therefore we should reflect that fact by decrementing the things the reference counts of the things they point to, as shown here. And the result of this is a cascade. Now all of a sudden the lower left object, this one here, has no references, and so it's going to go away. And that's going to take with it, and as you can see, it's obvious that that's going to take with it the rest of the list. So automatically this list has been freed when its last use goes away. So there are two things that happen. Well, there are two occasions on which this happens: when you assign to a variable, when a variable goes out of scope, or when you assign to an existing variable, you may free up some storage in either of those cases. What else do I have to... All right, so this is actually only part of the story. Where else do I have to manipulate reference counts? Just on the basis of how this works, where else would I have to manipulate a reference count? Any suggestions? What am I missing? I've taken care of variable assignments. I've taken care of freeing of variables or deallocation of variables. And what am I missing? Yeah.
Allocate, create, setting reference count to 1.
Well, right. You don't free them, but that's right. When you allocate, you have to have. Well, that's an interesting question. How should we handle allocation? Okay, so we allocate something. That's a little tricky. So we allocate something, and think about the sequence of events. What's the first thing you usually do after you allocate something? You assign some variable gets that pointer that you just allocated. So if we allocate the thing and we set it, what should we set its reference count to? If we set its reference count to 1, then when we assign it, its reference count will be 2, and it will never go to 0. So allocation is a little bit tricky, and what you do is, or what you can do is something like start out with a reference count of 0 and hope the thing gets assigned, or have your system set up in such a way that you know that when the thing gets allocated, it will always be assigned somewhere. And there are you have to be a little bit careful about that special case. But I'm still missing at least one example where I've got to manipulate reference counts, at least in this, according to this model so far. So allocations, we have to do something. Assignment, deallocation of storage, variables going out of scope or being deleted by a free by the reference count going to 0. One more thing, at least one more thing. Oh dear. I'll tell you this, any systems you guys build will crash and burn fairly quickly. Yeah? Yeah, well, that's what we did here. So when when this object went away, we lowered the reference count of the variable it pointed to, 0 here. Likewise, when we leave the procedure that defines x and y, we would have to lower this reference count to 0. Right. That's sort of a hint. Actually, there are two other things. Two things we're missing. Okay, that's all. I'm forgetting. Two things we're missing. Two operations that programming languages do where the reference count must be manipulated in order for this scheme to work properly. Yeah.
Whenever you return to a function and stack pointer, all the variables that were free by being in stack, you need to go through and free all of them.
That's right. And what else? There's something else you have to do on a return. Yeah, well, we'll assume that freeing includes the recursive bit, yeah. What other considerations on a return? Well, suppose I want to return, suppose that we've now reached the end of the program. And my statement and x and y are local variables in this procedure, and my so this list down here will have disappeared by this time. And I want to do a return, not a return, I want to do a return x. How is that going to work? Yeah.
So you're returning something which increment its reference.
Yeah. Now. So you increment its reference count, and if I then, now we get something tricky because let's do the scenario, do the simulation in your head. We increment its reference count, we return it to maybe something that says x equals f of blah, blah, blah.
So assignments would have to say it's coming from a function and don't increment its reference count. Or maybe decrement it and then increment it from the variable.
Yes, that's right. You can think of, so in other words, we have to consider a function return value as being itself a temporary variable that gets, which it is. I mean, it's like the variable EAX if you want to think of it in machine language terms, but it's this variable. It's going to disappear immediately after the statement containing that function is done. But until it does, it's a variable, and that means that when you assign from it, when you assign a variable value from it, you have to increment the value of the reference count, and when you deallocate the variable, you have to decrement the reference count. Okay, one more thing. There's one more thing that we have not mentioned. Yes? That's right. The parameters, when you pass the parameters, you are in effect creating a whole bunch of variables, and each one of these, you're assigning the value of the parameter into it. So you have all of these things, and so that's good. Now, so some of this can be, if you think about it, you'll soon see that in many cases you'll be doing things like, all over the place, you'll be doing things like increment the reference count on this, decrement it. Increment it, decrement it immediately. And as, for example, when you do a function return. So there are various optimizations that you can imagine performing that avoid having to do reference counts too often. And for example, one of which is people will go to considerable lengths. They'll do things like save up all of the freeze for the end of a module or something like that. And when you don't bother to modify reference counts on local variables, there are ways that you can avoid modifying the reference count on on things pointed to by local variables if you put off freeing until you're at the end of the block. So there are various tricks that you can do, but this is sort of the basic idea, and it's pretty nice. Now tell me, does anyone know enough C++ to tell me how would you do all of this at least semi-automatically in C++? What would you do? Who's done it, by the way? Who's ever done something like that in C++? Ah, okay, good. Well, then that means we're talking to experts. Yeah, how about that expert in the back there? The constructor and destructor of what? Okay. Okay, but I don't see how it gets, I don't see, so I've got it in the class, but now I'm manipulating pointers to those objects. So when I do a pointer assignment, how does that, how does the... Well, you can't quite do that in C++, but yes, you have to basically, you have to invent a new class that functions like a pointer, so that you can, so that you use it in place of pointers, and every time you assign into it, it does this pointer manipulation, it does the reference count manipulation. And every time it has a destructor, every time it's freed, it does the necessary decrementing and so forth. And surprising, there's a lot of C++ semantics whose effect appears to be to make this kind of thing work. It's subtle, but it's all in there to make this kind of thing work. An interesting interaction between language design and the things you needed to do. I mean, language features and language design. So, for example, in C++, you can define what unary star means. Star me. You can define what that means. You can define what the arrow operator means. Right? Within certain limits, you can define those things, and it's all. And of course, you can define constructors and destructors, which actually introduce a lot of interesting complexity. All right, so that's all very nice, but as I'm sure you're aware, there are certain weaknesses for reference counting. It uses up a certain amount of space, but then all of these methods do, actually. It does a lot of just simple pointer assignment requires memory traffic, because assigning pointers that you're holding in registers, you have to go in and look at the reference counts and do all that sort of thing. So there's quite a bit of activity that has to go around. Even very simple operations like passing a pointer to a function or assigning pointers. And then, of course, there is which I'm sure you're all aware of, there is a big problem with reference counting, which is circular data structures. Yes, if you have a circular data structure, then they sort of, it's like a ring of criminals who are all giving each other alibis. You know, they just never go away. So you have to do some. So there are various schemes for doing that. They talk about weak references. You can do fancy things, or you can just be careful to always cut the circular links. You might say, well, circular structures are kind of rare, but in fact, there's an extremely common use of circular structures, which is what's a data structure? A very familiar data structure that is circular, even though it doesn't look circular. Yeah. A doubly linked list. You go forward, back, forward, back, forward, back. That's a circularity. You don't think of it as a circularity. You think of it as a doubly linked list, but to the system, it looks like a circularity. So there's this question of how you deal with that, and there are all kinds of schemes that have come up to make all of that work nicely. But you could also just attack the problem head on and do something that can handle circular structures, and that goes back a long way. I don't know whether reference counting came in first or this mark and sweep garbage collection. Mark and sweep garbage collection came to us originally, I think it was originally in Lisp back in the 50s. Yes, Lisp is that old. Lisp is almost as old as Fortran. I should probably look up the history on this. I don't know what all the history is. Oh, by the way, there is, you will see reference counting implementations. It's not as if this thing is unused. Those of you who have dealt with the Apple, what's the name of it? Cocoa, I guess, that Objective-C stuff, they used reference counting, and you have to be, and there are these, to the newcomer who's never heard of it, there are these obscure passages in the documentation about how you have to be careful on handles and all this sort of business. It's all very interesting. But there's another use of reference counting in the Unix file system. So Unix, when you do an RM, a remove of a file, it doesn't, in fact, remove the file. What it does is it nulls out, in effect, it nulls out or removes a pointer to the file. It's not called a pointer, it's called an inode, or an inode number, and it removes that from a directory. And what happens is that the file system treats this as a kind of assignment and does an increment or decrement of the reference count on the inode, on the file, on the structure representing the file. And when that goes to 0, away it goes. Which is perhaps a reason why they're kind of careful not to let directories become members of themselves and stuff like that. There's certain rather disastrous things could happen. Well, leaks could happen if you did that. Okay, so here is mark and sweep garbage collection. The idea is very simple. We pull. This is straight out of CS61B. We do a graph traversal. I mean, look at that. Isn't it obvious to the nearest, to the rankest amateur that this is a graph we're looking at here? An unconnected graph in this case. We have at the left sort of the basis of the recursion, if you will, all the so-called roots. So the roots are all the things that all the things that a program can use to get at to get directly at a certain pointer value. So they include all the named variables, which could be on the stack or could be in static storage. And they include, so those are the basic things, the named variables, the things that you can get by naming. They also include things like that you don't get by name but have function calls that get them. For example, in Java, there's something called, current thread, I think. It's a call. Static function, and that's basically giving you a reference. So somewhere hidden down in the bowels of the runtime system, there is actually a variable that gets returned by that function. So even though it doesn't look like a variable to the programmer, it really is, and the runtime system has to be careful to take that into account. So those are the roots, the places that you start. Those are all the things that your program can directly reference, and then you find all the things that you can indirectly reference because of those things that you can directly reference. And that's a graph traversal. You just traverse this graph, and when you do that, you will find all of the storage that you can reach from these roots. It's a reachability thing. You do a simple depth first traversal or breadth first traversal, say a depth first traversal. And when you're done, you will have marked all of the places where that are used. So, for example, here we have a root that's pointing at B, and from B we have a pointer to D and to G, And obviously we somehow have to go back, when we wrap back to B, we have to have kept track of the fact that we've already seen B. So in this case, we color it red. Naturally, you can't implement it quite that way because it's too dark in the machine to see what color it is. But you can set bits and things like that. Okay, so we then traverse the route 5, which doesn't require us to do anything. Null doesn't require us to do anything. And here we traverse the route E, which quickly leads to something we've already seen. And at this point, let's look down here, which is where all the storage actually is. This is the storage all laid out from the runtime's point of view. And it's all down there. The green areas are free storage. And what it does is it says, okay, that's fine, I see this. I'll just look through all of this storage. I know the length. If I see it, if you give me the pointer to an object, there's somewhere I'm keeping around the information of how big that object is. So I can therefore start at the left of the lower address of the storage. I can sweep through the storage and find everything that's marked and everything that's not marked. And all the things that are not marked, I can add to this green free list. Like that. And at this point, now now all I have to do is make sure that I allocate from the green, and everything's fine. So the things that I swept over and found to be unmarked, I just did a manual free on them, a C++ style delete. And that's the idea behind mark and sweep. Very nice, elegant sort of thing. And all very good. Okay, at this point, why don't we take well, first of all, I'm sorry. Got to ask for questions, either about this material or anything on the project. I haven't asked about that. I actually see that there are people who have started the project. This is gratifying. There's actually a half chance someone might finish it, yes. It depends on the implementation. I don't. Oh, so the question is, how can we? What technique can we use to mark things without changing their values? Well, of course, first of all, it's not necessary not to change the values. Remember, these are objects that whose structure Java determines. So it could have arranged, for example, there are lots of tricks you can do. For example, one trick is to say, well, all pointers are on word boundaries, so those last 2 bits of the type pointer, maybe I don't really need them. I can use them to do marking or something like that. So you can use the tricks like that. Or, if you want to be nice and non-intrusive, you can instead have a bit vector that is a separate vector that contains, say, 1 bit per whatever the smallest unit of storage you can allocate is. And then so that will increase your memory usage by typically some small percent, like, for example, 3% if the smallest unit of allocation is 32 bits, and 1.5 or 1.6% or something if the smallest unit of allocation is 64 bits. You just have a vector that tells you all of the locations in storage, that's indexed by memory location and tells you all the locations in storage that are currently allocated. So either of those tricks will work. You probably don't want to build a dictionary and have lookups. Is this storage located? That probably would make garbage collection rather terribly slow. Everything else fine. Let's take a break. And here are the tests. Please keep them in order because you'll see a little number in the upper right-hand corner which corresponds to these lists. By the way, this class did a lot better on test 2 than my classes usually do, so. Yeah, actually, I was just about to say that this was not going to work too well. Let's see. Do not step on the whoozamajigget.
Key, is that what that is?
Yes. Please keep them in order.
Generous grading also. I think that may be why we.
That's always possible, yeah.
I was expecting like much worse. So Pi Nu. I didn't check the documentation on that. Had been updated in the comments, but it takes a type, a pi type.
Right. Pi type pointer.
Pi type pointer. And
Well, it is. I'm sorry. Pi type is a pointer. Yeah. It takes a pi type object pointer. Yes.
So how does it know how much space to allocate?
Because it contains a. You're supposed to create the pi type object is supposed to contain the number of instance variables, which tells you exactly how much space you need. That's why that field is there.
I see. Okay. I was asking about classes, like how you tell time and space.
All right, they'll still be here afterwards. So why don't we just continue on here?
Oh, thanks.
I say, why don't we just continue on? All right, good. So one of the features of mark and sweep garbage collection that you might notice is that the amount of time that you spend garbage collecting is proportional to the amount of storage, the total amount of storage. Why is this? Well, it's because you have to, you will in any case sweep the amount of storage here. Well, actually, it's actually proportional to the total number of objects, garbage and not garbage. So the marking phase is proportional to the number of good objects, and the sweep phase is proportional to the number of good objects plus the number of garbage objects. Well, plus free space also, you skip over that. So you might say, well, maybe we can speed this up. Now, careful though, let's do a little analysis. Just because we have to sweep over garbage doesn't necessarily mean that this is a big burden. So what tells you that there is a limit on the on how much, on what percentage increase your program, what percentage of your program gets devoted to garbage collection? So why is it that despite the fact that you may have minuscule amounts of non-garbage storage at any time and large amounts of garbage, why is it that the garbage collections that you do don't increase the running time of the program by some large factor? It's actually a simple argument. Yeah.
Every time you collect the garbage, it's gone.
Yeah.
So you only have to garbage collect once it needs a lot of garbage.
Well, right, because at that point the free storage will be allocated and you can skip over it. But imagine a program that does nothing but allocate something and then free it very soon thereafter, so that as it runs, it collects garbage at an enormous rate. Why isn't that fact, the fact that you will be doing garbage collections fairly frequently as a result, why isn't that slowing the program down a lot? Yeah.
This is garbage collection, so the actual act of collecting it, allocating it reasonably cheap once this fall is gone.
It is, no, it's not that cheap because you link things into the free list and so forth. But you're concentrating on the garbage collection. There's actually something else at work here. This is an engineering question, so you have to think, what are all the factors? Yeah. That's true, but you still will be garbage collecting an amount of time that's proportional to how much garbage you're creating. So it's one simple consideration. Yeah, you want to try? Okay. Absolutely, yes. You have to have done something to make that garbage in the first place. So you can't increase. There has to be a limit to how much you slow down the program, because in order for something to be garbage, you have to have bought it and crumpled it up and thrown it away first of all, and that takes work. So the garbage collection is essentially has to be balanced against that consideration. There's also the fact that when you do mark and sweep garbage collection, you generate these gaps in storage, which that may not be as serious a problem as you think, but one might think that it is. So here's an idea. Let's not look at the garbage. Let's just look at the good stuff. And since not looking at the garbage means we can't sweep, we'll have to come up with some different way of doing this. So what we'll do is we'll rearrange storage as we go along. So not only will we garbage collect, we will pack things together into a new storage area. And that way we will eliminate gaps, we'll eliminate fragmentation, and we'll also manage not to touch the garbage. Here's how it works. So we're trying to convert, so we have a bunch of roots. Here I have represented them in their storage locations, and here I've represented them with this graph structure. So these are two representations of the same thing. And this storage area up here I'm going to call from space. It's the space we've been allocating in. And here's what we do. We're going to start by following the roots. And when we follow a route, what we do, we follow all the roots. This is a breadth-first search. We follow all the roots, and we copy the things that they're pointing to, if they haven't been copied already, into a new storage area that we call to-space. As we do that, as we copy these things, we also keep track. We basically mark all of these guys up here with pointers called forwarding pointers to this new to-space. Now you might think about how you're going to represent all of that, since storing a pointer to something uses up a bit more space, but it can be done. So we store pointers to to-space from all the roots. Now we continue this process. We're done with the roots at that point. Oh, and as we copy them, we also move the root pointers to these new things that we've just created. Now we go through and we start at the left of this to-space, and we start converting the pointers that we have moved into to-space. So the first thing we find is D. We haven't copied that yet, so we make a copy of D, and we leave a forwarding address behind so that other references to D know where the new D is. And we continue in this vein. We see G, so we add G. Right? We see, and then we update G. So when we copy it, of course, we give it the new pointer. Now we come to D. Well, we've already seen D, so all we have to do with this D pointer is update it to point to the new location. How do we get that new location? Well, we left that nice little forwarding pointer around, a forwarding address, so that we know that that's where we go to get it. And so forth. We see G has already been copied, B has already been copied, so now we're done. And without looking at any of the garbage, we've now moved all the good stuff from the front space into 2 space. And at this point, we've swept through all of 2 space. We've caught up to the end. And so at this point, we can do the garbage collection proper. We can get rid of storage by just saying, from now on, all of our storage is in 2 space. The old from space no longer exists, and this is our space. Really nice. And it compacts everything and moves it at the same time. But this isn't good enough either, because typically you'll have a whole bunch of storage in your location that you allocate at some point and then keep reusing. And the thing about this is that this is going to keep sweeping over it or marking it and moving it, even though nothing has really changed. So, well, all right, I already discussed how roots work. So we can do a little trick, which we call generational. We use the fact that most storage dies young, and only some of the good stuff stays behind. And we can do this we can divide memory into young and old storage, or as we like to say around here, tenured and untenured storage, and untenured and tenured storage, and only sweep through or only mark the roots and so forth that point to new storage, and thus throwing away new storage that's garbage. You have to, obviously, if you think about it, that means you have to be careful, because it's possible to have old storage pointing to new storage, which means you have to keep track of, there's some complications where you have to keep track of where in old storage you might be pointing at new storage and do something about it. Now we've been talking about, and I should finally say, we've been talking about garbage collection as if it has to be perfect. And obviously all this would be impossible in C and C++. They just don't have the mechanisms around to know where to get all of this stuff. But what you can do is something called conservative garbage collection, a very simple, a very interesting idea. We just say, okay, I know that you've got C, so you can't really garbage collect this in the usual fashion, but here's an idea. Let's keep track of all the mallocs that you do, all the storage allocations that you do, and where all the objects that you've allocated really are. And then, to do garbage collection, what we're going to do is we'll just sweep through all of the stack and all of static memory, whose addresses we can find. And even though we don't know which of those things are supposed to be pointers, we can look for all the things that look like they're pointers. In other words, that happen to be addresses of things that you've allocated. And we can say, oh, this must be, let me assume this is a pointer and mark this thing. And since if I do mark it, it doesn't go away, it won't be collected, this is a safe procedure. It means the only things that I will collect by this strategy are those things that don't have anything that even looks like a pointer to them. And so this conservative garbage collection, you'll see there's an open source implementation for C called the Berm-Weiser collector that does exactly this. It's a kind of a convenient idea. Well, I've taken you over time, so let's end it right here. And I'll see you. And I will give a short summary on Friday is HKN Day. So those are important, so do come for that. And it's also, I will give a short summary and then throw the floor open to any questions about anything that you might have on all subjects having to do all of human knowledge from the beginning of recorded history, with particular emphasis on the content of this course.